start with the session of the morning, the first plenary talk. So it's my great pleasure to introduce Professor Claus-Dieter Ohl from Magdeburg University in Germany. So Professor Dieter Ohl, he did the PhD with Lauterborn, right, at the University of Göttingen in bubble cavitation and similar topics, if I'm not mistaken. Then after this PhD in 1998, he moved to Johns Hopkins first, I guess with Andrea Prosperetti, to do a postdoc, and then he did a second postdoc with Delbert Losse at the University of Twente. After that, he spent like about 10 years as a professor in Nanyang Technical University of Singapore, and after that, he moved to where he is currently, Magdeburg University, where he chairs the soft matter department, okay? He's going to talk about cavitation, of course. Thank you very much.
Thank you, Xavier. Thank you also for introducing the subject yesterday evening. It was a very, very fun presentation. You mentioned that I started with Andrea Prosperetti, and actually I didn't know any fluid mechanics when I joined his group as a postdoc, so it was a tough start. But now I think by the time I learned a bit. Why I moved to Magdeburg is maybe you know that device that is a vacuum pump, and the name giver of our university is Otto-von-Guericke. He actually developed this one for sure for war reasons. If you are running out of gunpowder, you can use vacuum to propel bullets, right? So how to demonstrate that the vacuum is good, like you did yesterday, the bubbles are good. At that time, they did do big experiments, and maybe you all know this experiment. This is the horses, they're pulling at a small bowl or a steel sphere, which has been evacuated but not bolted. It's just the pressure difference which keeps the steel sphere together, and they pull at it. And I would think this is the founding or the start of cavitation research, because it was an empty sphere surrounded by a high pressure region, but it was not really allowed to collapse. So it was just a first demonstration. The work I present today is done not by me, but by all the other people. And I'll even show some work which is done in a completely different group today. I will introduce the people then later on. So for today, what is a bubble? And in a bubble in a liquid is actually something which is empty, and it is surrounded by a surface, an interface where some interfacial energies might be related to it. Inside the bubble is either nothing, but that's the most easy case, but it doesn't is not reality, or you have some gas or vapor or both of it. Outside you have a liquid, and then the most simple case you can describe the bubble with a time-dependent radius, and what are the boundary conditions are you have a far field, or you have a pressure as a function of R and T, or the easiest thing is to go very, very far from the bubble and you say, okay, I have defined a pressure which is not influenced by the bubble itself. That would be the pressure at infinity. And you can use this one to drive the bubble, or you say you have inside a bubble which is more or less empty, and then the far field pressure will drive this one to collapse. In 1970, Lord Rayleigh and later on Blessed have found a solution for this problem by looking at the dynamics. It's a actually pretty simple equation. However, it's already nonlinear. And only a few years back, some Russian genius have found an analytical solution for this equation, which I was really, really happy to see that. But it works. This one works for if you want to sink a ship with an underwater explosion. It works as well as you want to penetrate the blood-brain barrier with microbubbles. So this equation actually holds as long as the bubble is spherical. The bubble is more or less an oscillator. If you drive it not very hard, you can find a harmonic response of the bubble, and that is the result from Minayat. And what is something for water? You can remember that the resonance frequency of the bubble times the radius of the bubble gives about 3 meters per second. So the millimeter bubbles are in the kilohertz or sub-kilohertz range. And if you go to micrometer bubbles, you're in the megahertz range as a response. And these are these megahertz bubbles. They're used as contrast agent, very small bubbles, and you can drive them right with the diagnostic ultrasound, and you get a big response. So these are nicely used. If you want to do some more harsh thing, you can drive them very hard with a sonotron. Then you're outside this linear regime, And these bubbles, they are doing a lot of things. You see only the scattered passes of these bubbles. They move, they oscillate violently. They can create chemistry, they can mix, they can emulsify. The most spherical bubble was found actually more or less by accident. Nobody actually believes that you can do that. It's called the single bubble sonoluminescence, and that was a time when I did my PhD. At that time, it was really hyped. And what you could do is you can strap a single bubble in the center of a flask and you drive it, and you don't destroy the bubble. You can drive it extremely strong. And during bubble collapse, the bubble emits shock waves. Yeah? So here's a picture movie of a shock wave emitted by this bubble. And this is the radius time curve. So when the bubble, the pressure, this is the pressure here, the other one is the radius. Pressure is low, the bubble expands, the pressure recovers, and then the bubble is driven by the external pressure, and then you get a very strong collapse. And tell you, nobody knows what happens here. But you can see light emission, and you get energy concentration. That means energy per volume of 10 orders of magnitude. And there's a company here in UK which uses that for making fusion. So there is actually a lot going on in the spherical bubble collapse. So that's where I come from. Professor Lauterborn, already in 1975, he invented the following. He used the laser, focused the laser in the liquid, and when the laser is actually focused, you deposit the energy of the laser, you ionize, or let's see, just heat up the liquid locally. The laser pulse is very short, so the fluid mechanics is completely decoupled from the energy input. What happens is, you see there's a bubble formed, and then it expands, and then it collapses again. Here is about the collapse. I think the recording is about with 70,000 frames per second. At that time, it was really extremely high speed and painful experiments. These were photographs. They have to be developed. If the experiment didn't work, you put a lot of money and time into it. But what he saw is that the bubble, when it collapses here, between here and then here, it forms a protrusion. And the reason for it is that there is not in a spherical environment, but it's a little bit disturbed by a boundary. So a boundary doesn't allow the bubble to shrink spherically convergent into one focus, but it creates a pressure difference between the top and the bottom, which accelerate, and that is again a nonlinear process. You focus a jet, and we have seen a nice talk about jets from Jose. A lot of fluid mechanics goes on between here and here, and then there's a liquid flow going down, and that pulls at the gas phase, and what you see is you don't see the jet really much, but you see the gas, the liquid which pulls at the gas and vapor phase and makes this fine structure. It is always towards the rigid boundary, and because these bubbles were known, these bubbles were known to create erosion. What was then the interest was, is this jet actually able to erode surfaces? And we saw yesterday nice pictures of erosion. And this jet will not do much because it's too far away, but let's put the bubble a bit closer and see what happens. And this is a simulation of a bubble, axisymmetric simulation of a bubble expanding and then collapsing. You see it becomes an X shape, and then it forms a flow from the top to the bottom, which hits the lower bubble wall. So nothing actually happened to the boundary yet. But then, these are also some snapshots. So this wall breaks off. You get a jet coming down. You get a splash going upwards. The splash goes further upwards. You get some nice instability, Kelvin-Helmholtz instabilities. And you get the flow, which you don't see here, but the flow moving over the surface. So the surface is really here. Okay. The surface is here at the bottom. So the bubble is much closer to it. And these are the bubbles which do something to the surface. We see here now the re-expansion of the bubble. And you can imagine that there must be a flow driving here the gas outside. And then the bubble re-expands, collapses, and drains some droplets. Yeah. It's really interesting fluid mechanics. What I find really extremely interesting is the initial condition is extremely simple. You put a bubble near a rigid boundary which is stopping the flow. And that is the result. It's the flow developing out of it is so marvelous, complicated, that you can get generations of fluid mechanics people can work on this. We worked on the shear stress. So this is the flow. These pointers are showing which direction the flow goes. And this is the color, which shows the velocity of the flow. And we are just looking at, from the axis to the stagnation point here, outside. So this is a radial coordinate. You can just think about mirror to the other side. And we see that we get a very, very fast flow at the moment when the jet comes down. And then it spreads over the surface. You see also shock wave emission by quick jitter of the motions. And on the bottom, this is the wall shear stress as a function of distance and time. So nothing actually happens, very low, few Pascal, nothing actually happens. You have stagnation point, and then you see this peak here coming out, and it brooms over the surface. But you don't really see is how big that is. So it's just a reminder, but I don't think you need to do that, but it's the wall shear stress is that you take a velocity gradient, multiply it with the viscosity, and we get typically about 1 Pascal, 1 kilopascal, something like that. And then when the jet impacts, you get 100 kilopascal, and that is something like, for water, 1 micron above the surface, you have 100 meters per second of flow. So it's enormous. I'm not sure if actually there's something else going on. There's no slip boundary conditions, so maybe it's not perfectly true. But it's enormous, and then you see it's going up here very high, and it moves over the surface like a broom, this shear stress. And that's how these bubbles are able to clean surfaces. When they collapse, it's not the shock wave or not the outer flow, but it's actually the shear stress generated by this jet on the surface. You can do these nice graphs. I love them. So here we see the time. Okay, sorry. Here we see the time. And on the vertical axis, the position from the stagnation point. And the black line is the bubble radius as a function of time, the volume equivalent bubble radius as a function of time. So the bubble expands. Here is maximum size. Here it collapses and re-expands. And then we plot the wall shear stress on a log scale in positive and negative direction. So this is a outwards flow, a shear stress going outwards. This is a shear stress going inwards. And nothing actually is a lot happening. If it would be spherical, you get a bit of an offset, but nothing happens. But then, when the bubble collapses, you get this dark blue, dark red colors, and this is where the shear stress goes up by this enormous magnitude. Here, we have a lot of effects on the surface, which you can use then maybe for practical applications. So, I was wondering if that is true or not. I still don't know. I measured it, and I got 2 orders of magnitude lower shear stress, but I didn't find a device which is able to capture that correctly. So I think it was the problem with the measurement. I trust the simulations much more than the experiments in this topic. Actually, this is another experiment where it was 2 walls, a bubble near 2 walls. I think I sent this paper to Jose. The referee said, this is a lousy paper. Er sagte noch, Jose, have a look at this figure. Actually, I was amazed how good the simulations are already. This is open foam. It's nothing very complicated. A PhD student did it during, after 2 years or so, he was able to run the simulation. But he's also pretty good. But really, it's on the time, perfect on time. It's perfectly on the shape. And it captures compressible effects and viscosity, surface tension. So everything is in. So you don't need really to do experiments anymore. You just run the simulation and you get all the fluid mechanics out of it. And I'm talking as an experimentalist. Sorry for that. It's not the case. Otherwise, I wouldn't be standing here and talking to you as an experimentalist. There was a new kind of jet. And again, it came from simulations, yeah? But not our simulations, but a group of Christiane Lechner, Lauterborn, Koch, and Robert Mettin. And what they did is they put the bubble very, very close to the surface, and they didn't get this broad jet I showed you, yeah, this very wide jet, but they got this very tiny jet here in the simulations. And the jet has 1,000 meters per second. The one I showed you before had 100 meters per second, typically. Yeah, so order of magnitude in water for the pressures we use here. Funny. So, is that true or not? And 1,000 meters per second, you could imagine that this could actually erode the surface. Maybe, maybe not. But so Fabian Reuter in my group, he was able to capture this jet. And it's not trivial because it's very fast, 1,000 meters per second. So within this maybe 100 micrometers, the jet happens here. But you really need to capture it correctly. And then you have motion blurring. That's the other thing. So if you even have a 100 nanosecond exposure time, which is short, you would not really capture the jet. You need much shorter exposure times in the order of picoseconds. So we use a device, a fast camera, but we use a pulse laser with sub-picosecond exposure times to get these clear pictures, where you also see shock waves. So the first upper part of the bubble, so initially the bubble is really round, it's a hemisphere. Yeah? This is the last stage, the last few microseconds, or this even here, the collapse is here at 600 nanoseconds, less than a microsecond before this jet happens. We have this shape of bubble, the top, then this, you get a singularity at that point. The liquid rushes from the side and creates a stagnation point here and shoots the jet upwards and shoots the jet downwards. And that, you can't really see the jet, but you can see it, but it's inside a bit hidden, but they see some droplets from the spraying process. And if you look a bit more careful, higher magnification, this one collapses here, creates then this jet downwards, and then we are not collapsed yet. So the bubble actually hasn't collapsed yet. That's interesting, we get a fast jet, but the high pressure is still not there yet. This is when you look from below. So this was a glass plate, and you look from below, and you see these structures inside. So the jet comes in, and then it creates a spray, and the spray is visible as droplets. And now this is a movie. Is it moving? Okay. It forms a singularity on top, you get a parallel flow, and then the whole process is over. Okay, so that was also predicted by simulations. And there you get the shock, the main shock wave coming out. And then you look from below, and things look not anymore so symmetric as it was before. And that is the key. The title of the talk is about erosion. And a non-spherical bubble will lead to erosion. However, there is not a spherical bubble. I showed you this most spherical bubble for solar luminescence. Yeah, if you take great care, but these bubbles near a boundary, they're never spherical. And additionally, you have bubbles nearby, you have gravity, you have other effects, which I'll show you in a short time. They lead to non-sphericity. So it looks pretty spherical or axisymmetric. The jet comes in here, but then you see this kind of structure and shock waves coming on that way, and they don't look anymore axisymmetric. And if you zoom in now, these are multiple experiments, but they're put one after another, that they're in correct timing. About 20 nanoseconds between two frames. Exposure time enormously short. So there's no motion blurring going on. And you see, this is the jet. So we look from below. The jet is inside. This is the needle jet, the fast jet, coming in here. The torus around it is collapsing, and it collapses on the bottom first. It collapses further. It goes up. You see a lot of shock waves coming in. And then all the shock waves, they meet at that point. And then you get this this very strong visible shock wave from the images. And what happens there? So what we think is that these shocks actually amplify while traveling over the torus, and then they meet up. They form some caustics, and they meet up on the top part. And at that top part, where you get this very strong shock, we have maybe something interesting going on. And this is the result of the surface after 1,000 bubbles. At the same spot, the same bubble taken. And here we see erosion. So I think it was a silver single crystal. We see a little bit of happening here, something's happening there, but mostly is there. And this is the torus. So the torus is sitting there, and the erosion is happening there, off-center. And then you can look for the topography, and you see not much happening there, and we can't actually go deep enough into the hole. This might be 100 micrometers deep, this hole. So,
Can I ask a question?
yes, please.
Is this air and water?
Oh.
Are there air bubbles in water?
Good question, I should have told you. Yeah, so these are laser-generated bubbles. And what you do is you vaporize you vaporize the liquid, and you form then some species which you don't really know what they are, but most of it actually goes back to water vapor. You also have a low pressure inside the bubble, and you diffuse some of the gas in the liquid into the bubble, and that cushions the collapse. So you have gas and vapor inside. Okay. Right. So actually what I did is I showed you the wrong presentation. That's why maybe I'm a bit you're laughing, but this might happen to you too one day. Okay. Soft and hard matter. This is okay. But it's very similar. I always talk the same stuff. Okay, this was erosion. Okay. Okay, now let me continue here. Is that coming? So again, Professor Lauterborn and Achim Philipp, I didn't put it as a JFM from 1998, it's cited 1,000 times. They looked at the erosion as a function of gamma. I didn't tell you what gamma is, but gamma is 0 if the bubble is a hemisphere, and infinity if the bubble is in a spherical environment. So it's a normalized distance of the bubble from the boundary. So the closer you go to the boundary, the more erosion you get. Looks nice here. Achim Philipp was doing his PhD while I started blowing bubbles at that time. His PhD was about looking what does a single bubble do to erosion. And he measured the erosion and saw, yeah, if I go closer and closer, nothing actually happens, and then something happens. A lot happens. But he wasn't really sure, is this the plasma, because you shoot a laser and you're very close to the surface, is that the plasma, or is this the bubble, or is it something else? So we looked back and did this simulate. Now the experiment's very much closer. So we are not going 0.5, we're going smaller, 0.5 to 0. And we see no erosion, actually, for 0.5. So they see erosion. The problem was probably the plasma there. There's no erosion happening. And erosion only happens, gamma 0.3, only very close to the bubble surface, and only when you have this needle jet. But it's not the needle jet which creates erosion, but it's this shock amplification on this torus. And this is universal, what material ever you take. You only get erosion if the bubble is sitting on the surface and has this non-spherical collapse with shock amplification. And now I steal some slides from a former PhD student. He's now professor in Sanya, which is a dependance of Harbin University. And he did the simulation. And not only did the simulation, but he found the origin of the asymmetry for the experiments, which fit now very nicely. So if you look back, the bubble is generated by plasma. This is the plasma. It's a very small scale, but it's okay. This is the plasma. There's the bubble generated. This is the shock wave which removes it. And then the bubble expands very spherical. But initially, the plasma is not spherical. And he said, okay, let's start a bubble. He doesn't do the plasma thing, but he starts a bubble with some sort of an asymmetry. And so now you have to do 3D simulation. He uses open foam, 3D simulations. And he said eta is this aspect ratio of this sphere with a cone on the side. And he changes that one. And here's a movie result of the simulation. So it's a 3D simulation. And you don't see much of the 3D. It looks very asymmetric, but at the end there's a little bit of asymmetry. And you compare that with the experiment, and you get excellent agreement up to the collapse. But then what is much more convincing is we're looking now from below and compare the simulation with the thing. You get actually the same thing. You get a center jet, the torus, which has a similar shape, orientation also. And then it starts to collapse on this side first, and then travels further. So from the side, you see also, you can do all these things. And what he sees is that initially you get a shock, which we also see the shock, or high pressure emitted from this point, and then the bubble goes further. You see the color goes up here. So this is here the color goes up. And the last stage you go up to 5,000. And he did the following. He changed these eta parameters, so made it more asymmetrical, but this doesn't really help. This is the pressure at the bottom where the first collapse occurs, and this is where the last collapse occurs. And we get a very strong collapse at the end. So this simulation somehow confirms that there is a shock amplification going on. And what I like a lot is that this can be done. Okay, you have need the right computer, but it's not really a specialized software. You can just download it and run that. You need and you get already the right physics or the right fluid mechanics out of it. And this is 3D. So we could now think about how do we have to prepare the surface such that this does not happen. This way we would be able maybe to remove cavitation erosion, or at least start with thinking about how to avoid cavitation erosion. We had then thought, okay, just for timing, we had a look how strong is this energy focusing. And you remember sonoluminescence, you saw they get light emission if you have a strong collapse. Maybe there's light too. Unfortunately, I didn't think that there will be light. This is during my PhD, or part of my PhD. We looked at that time of the light emission from a single laser-induced cavitation bubble and changed again gamma, so the distance from the bubble from the boundary. Very far away, you get a lot of light, and then at gamma 5, so it's 5 radii away from the surface, so this is this very weak jet, you get hardly any light. Below, no light. So you would not expect that there's light coming out. This was a picture. Oh, it's very dark. The light is somewhere created down. You don't see that here. But we have now a bit more tools at hand. We put in 3 cameras. So this is a normal photon camera to look at the bubble, how far it is away from the boundary. Then we need a camera which zooms in into this last stage of collapse, which is only 100 microns. So you have to use this. This is a Shimatsu high-speed camera. And the camera looks on the same spot here as this camera. This is a devil. Actually, it's not really a camera, but it takes recording when light comes. So it's an event register. So you can measure when the light starts and when the light stops for each pixel. So each pixel, and you can take it with a nanosecond resolution. So it's an extremely high-speed camera, but you only get light on or light off at each spot. This is used for higher energy physics. We got it for free for 2 weeks. So that is the setup. Additionally, this is an experimental talk. So if you're interested in an experiment, the laser creates a plasma. You don't want to put it on any of the camera, especially not on the sensitive camera. So there's an image intensifier here in front, which gates the light. So you switch off the light with this image intensifier before, only after on you switch it on when you want to look at it. Also with the lights for the illumination, you have to be a bit careful. You have to take out the illumination laser, but there's a pulse laser, so you can take out that out of the spectrum. So you get all the spectrum except for the light from the laser. And you look at the same spot with a high-speed camera and the image intensified camera. So automatically these pictures are correlated. That is the result. Remember, this is the torus. This collapse starts at the bottom and it ends on the top. And exactly there we have overlaid now the light. And it's exactly at the spot where you get erosion. You can have the asymmetry depending on the shape of the plasma, also on the bottom part. So your shock starts in the bottom and then goes down this. There you get also light emission. And sometimes you have the asymmetry a bit weird. You have more or less they come at the same time. So maybe the collapse starts from the side and then they amplify here, and here you get 2 spots of light emission. And with this nice camera, we can also look at what time the light emission comes. Here, it's not so interesting, but here, where we have 2 light emissions, they happen here at different times. The time is color-coded. And if you put the number here, 1 is the first light emission. The shock has traveled already a little bit further than the bottom one. So this has the first, and this is the second. The time is, the time is about 20 nanoseconds between the 2 light emissions. That's the time the shock needs. So they're separate from each other. You also see that there are 2 shocks visible. We use 2 laser pulses, and we hope with that one we can measure the pressure. We know the timing of the 2 laser pulses, and then we can measure the distance they have traveled, and out of this we can probably measure the pressure, because the prediction are about 10 kilobar of pressure at the end. Whatever equation of state was used in who knows? I don't know. Maybe it's wrong, but would be good. It should be somewhere close to the Young's modulus of that material. Okay, I have a bit of time, and I've said that I will also talk about soft matter. why I'm interested is the following experiment. Sunday, soccer, header. I don't think it's good to play American football and don't do a header when you're young. But so what can happen? This is not a real brain. This is a phantom, and this is an impact. Maybe it's not perfectly right, but what you already see in that movie, when it comes down, this impact is the brain phantom. You get cavitation here on the top, and if you look carefully, you got also shear waves traveling. I can run it one more time. So this impact, and then there are particles inside, and you see the particles, how they move. And so you can have, when your head is exposed to shocks or impulsive accelerations, you can form cavitation that is supported by evidence, medical evidence. You can also, can lead to brain injuries, traumatic brain injuries. And one of the major causes for death is not actually death on the battlefield for soldiers of the US, but death at home, coming back with traumatic brain injuries, and then they commit suicide. So that is, and the soldiers, unfortunately, they're only protected by earplugs or Mickey Mouse, but not really protected the brain from impact of shocks. And there can be a lot happening in. So I think this is an interesting area to study, but I'm a physicist, so I don't need to do the real thing. But we started some time ago and looked for what is the effect of cavitation inside a soft elastic material, because then you have a restoring force which you don't have in a liquid. We started with Yoshi Tagawa, when he did a sabbatical a few years back. He didn't have this nice high-speed camera he showed you yesterday. This was also a high-speed camera, but we couldn't really measure the stress compartments, or the magnitude and orientation. It's more like a demonstration that stress is generated. It's a polariscope. You do circular polarized light, and you linearize it, and then you look what happens to that. So this is a bubble in a bright field illumination. The collapse is more or less spherical, and this is the same bubble or similar bubble in the gelatine, and you see this bright spot around it. This bright spot here. This is where the shear stress is generated, or stress is generated around the bubble, and the spherical bubble generates more or less stress, and then the stress goes away. Spherical bubble is here plotted, and what also you can say is spherical bubble is always a bubble which doesn't move. So this is the center of mass. It just moves a little bit, but it doesn't really move a lot. So if there's non-spherical bubble, they typically move. So the stress is confined around this bubble. I wanted to show you some equations. You can use the Rayleigh-Pleasant equation, and you add another term here for the elasticity, and then you can account for the stress in spherical environments. There are different kinds of materials you can plug in. There's a very nice paper from Eric Johnson's group, and seems to work. But talking now, this is a bubble which is also expanding. Okay. But it's not perfectly spherical right from the beginning, and you see it moves a bit around. And this is a similar bubble. It's not the same, but a similar bubble. And you see it moves a bit around. And you see something is moving away from the bubble. So it's not confined anymore, but actually you can create waves, shear waves from that object. So the experiment we did with Yoshi was a bubble near a free surface. So this could be skin. This is air. This is gelatine. Bubble expands. The stress is confined around that bubble. But then you see there's a strong stress generated here. While the bubble moves downwards, a free surface, the bubble moves away from the free surface. You form a crack on the top, and you see this dark stripes, left and right, moving outwards. And so there's a lot of things going on. You confine stress because the stress waves are very slow, a few meters per second, so the stress can't leave that region. You build it up. Bubble pulls, and it goes downwards, it pulls at it, and at some later time, it relaxes through expansion of the shear waves emitted from that one. We did some simulations. This is very early. I don't want that. Let's talk about it. So a shear wave is a wave which has an amplitude which is normal to the propagation direction. So it propagates downwards and it oscillates sideways. And the nice thing is if you know the shear wave velocity and the density, you can actually measure the elastic modulus. And for medical application, that is very nice because you have different tissues have different elastic moduli or shear moduli. Particular cancer cells, they are from more compact region, and you can localize with just with ultrasound, or if you are able to do it with ultrasound, you can measure the shear elastic modulus by measuring the shear wave velocity. We did these bubbles in gelatin at different distance from the boundary. You see the bubble collapses very nicely. It moves downwards and then it goes up again, the restoring force. Here the bubble also collapses, creates a jet, but then the bubble is pushed up again. And here, very close, you get a nice bubble. So the dynamics is nice. We wanted to know now what is the shear wave generated. We are only looking at the upper part because we have to shoot the laser through that. And we use particles. You don't want to shoot the laser through the particles. So we see only there's a bubble generated, boundary is down there, but here we see the movement of the particles, and we can reconstruct the motion of the shear wave out of the motion of the particles. So it's a sideways motion, and if the bubble is created closer to the boundary is actually here now, you get a shear wave which travels upwards. And this is the summary. We get for different distances, gamma, we get either an upwards direction or a sideways direction. And we think the following is happening. The bubble further away, it moves actually more closer to the boundary. So it moves downwards, and then the wave is traveling orient is perpendicular to that. The same when you're at the boundary, you can't move downwards, but you shear the sideways. So you have actually the opposite, you shear sideways, and then the propagation direction of the shear wave is upwards. And in between, you have two motions superposed on top of each other, so you get a superposition of a shear wave moving sideways and a shear wave moving upwards. And that's what we have seen there. So, maybe 5 minutes. Coming back to the brain, this is work in progress. Sue1, my wife actually works on this project. And we are interested in what happens to the brain when we create cavitation in it. And this is just the start. We have here a slice of brain from a cadaver, mouse cadaver, embedded in the gelatin. And you see nicely the bubbles here, and then you see nicely propagation of a wave through it. Actually, you can enhance it a little bit. But you have actually a bubble collapsing here. We assume that something like you have a rigid boundary, and then here's water, and then on top is the brain. So it's a bit like the little interstitial liquid between the skull and the brain, the gray matter, and you get waves traveling through it. We would like to know, is this actually dangerous for the cells? If you put real cells, do they survive this propagation of shear waves? And here's another shear wave. Here are a lot of bubbles. We create a shear wave here at the bottom. And you see nicely how the shear wave here travels through this area of bubbles. This is just fun because in gelatin you can make bubbles and they stay there. So we create here maybe a dodecahedron bubble, so it's a platonic solid. And you can excite these bubbles. Oh, not this way. Maybe I've pressed a button here. And then you see this bubble oscillating. It's only fun. I don't know if there's any application for that. But you wouldn't find electricity if you build a better candle. Okay, no, there's actually one application is you can use these bubbles as a reflector, and we made this complex structure here, and then send a shock wave here from below and measured how much of a shock actually is. The shock travels through it, and create also cavitation. And you see there's actually not much of this wave coming through it, a little bit scattered through it. And we can look, this is the pressure wave without the bubbles, and this is the pressure wave with the bubbles, so you get about 1 order of magnitude of a reduction of sound field just because of this. And I would like just to end, maybe it's just a quick outlook. These bubbles in tissue are nice to watch with a high-speed camera, but it's not really practical, because if you're really interested, you would like to do them in situ, and you maybe want to use it for application for therapy. So you can't look with light in your body that easily. We worked on this high-speed acoustic imaging. So instead of using light, we use ultrasound and send the ultrasound pulses through your tissue and look if we can see bubbles. And bubbles are actually pretty nice. They reflect sound very nice. So you don't need to do a lot of beamforming. You can just send the plane wave through the tissue and look for the reflected acoustic path. It's called plane wave imaging. So you don't need to make a complex beamforming and long time for one picture. You can add multiple beams under different angles and compound them. And here's just a demonstration. This is a bubble rising in a liquid. You don't see the bubble, but you see the front surface of the bubble, so the sound comes from the left. And yes, these bubbles, they rise nicely up. And we can reach here already 40,000 frames per second using plane wave imaging. We don't see the bubbles, the size of the bubble, but we know where the bubble is. And we looked at, is that comparable with a high-speed camera? We made a bubble in a gelatine. We looked from a high-speed camera from above. And then from the side, we looked with the ultrasound transducer and using this plane wave imaging. This is the bubble, oscillates. And then this is the acoustic image. Now, this is not any more space, but it's time. But the speed of sound, you can relate that to distance. Then we get the reflections. We look for the related to the initial bubble size, and we get actually pretty good agreement between what you get from high-speed camera up to 70,000 frames per second. So you can actually do a single bubble imaging inside the tissue with this kind of technique. So that's it for today. So there's elastic bubbles. Be careful if you do that. So what I wanted to convince you is, show you, I'm convinced about it. Cavitation erosion is due to shock wave amplification. It's not the jet, it's not just a shock wave collapse or bubble collapse near a boundary. The bubble has to be exactly on the surface of the boundary, and the asymmetry must be such that the shock can be amplified while this torus collapses. Only then we have seen, for single bubbles, erosion. Doesn't mean if you have many bubbles, maybe there's something else going on, but for the most simple case, don't need any more these complicated theories about shock wave or high pressure impact, or then there are a lot of models for relating the fluid mechanics or pressures with the cavitation erosion. It's this process. It also offers a way that we can avoid it, but at least we can think about it, how to avoid this amplification on the surface. Can we have a certain kind of structure or elasticity or whatever which prevents these amplification? In soft matter, so in something, when you have cavitation there, you have on top of the normal fluid mechanics, you have also shear waves. And the shear waves are also fun to play with, and we can actually learn something about the properties of the tissue in which they propagate. And the outlook is that even in tissue, we can study bubble dynamics using high-speed imaging. This is just at the beginning. We're doing some bit more in this, other groups also. So we are not saying, okay, we can't look with a high-speed camera anymore. We can still use the tools of that. And therefore, I would like just to thank all the people involved. Fabian Reuter, he was actually the guy who found these needle jet experiments, and he looked for the erosion. It was really Henry Gracie. He just got his PhD. He did many of the CFD simulation in the group. Saba did this high-speed ultrasound imaging. Jay, I didn't show you that movie. It's pretty nice, but okay. Roberto Gonzalez, he left, but he worked along 10 years with me on cavitation. Julian Rapet started with cavitation soft matter. Yoshi started also with me during his sabbatical on that topic. My wife started with the brain. And we have collaboration. The thing I showed you on the light emission was done by Jaka Moore. He is working with Rob Petkosek in Ljubljana. And really want to highlight this 3D simulation. I'm really astonished that Jingyun was able to pull that off within a year time, to do this 3D simulation. They are non-trivial, but the code behind this is just open form. So I would like to come to an end. Thank you for attention.
Thank you very much for the talk. It was really fantastic. And I guess there should be some questions from the audience now.
About the erosion on substrate, on surface, you did not mention any wettability properties. We can neglect totally this contact line, stuff like that. It's so rapid, or do you?
Yes, you're perfectly right. There's no time to wet the surface. There's still a thin liquid film between the bubble and the surface. It's never wetted.
Okay.
Sometimes in a simulation, you have seen that, you're the expert on it, just to avoid, because sometimes the grid cells becomes too small, they have a boundary condition that it's fully wetted. So the water phase is there on the surface to avoid that contact line problem. But we have done experiments and have never seen that the bubble during the first expansion and collapse is able to de-wet the surface.
And then somehow there should be an optimal, maybe I missed that, there should be an optimal distance of the bubble to the surface, a bubble to the surface for the maximum erosion, or do you?
Yeah, I showed that graph.
You showed that, yeah. I think you showed there was a maximum, but is there any criterion for understanding that? Or?
Okay.
I think there was a curve.
Yes. Did I show this movie? Maybe
sure.
not.
No.
So this is a needle jet. This impacts now the surface. You see the droplets coming in. And now this shock wave starts to form around. And then this big shock wave comes out from that one. So here, as you see, there is a maximum. But I must actually be a bit cautious because we are getting very close here with the plasma. We do some optic tricks that we don't heat it too much. But we see around here, we see already surface melting. And you can distinguish the surface melting from the plasma with that from a bubble.
Should be a nice balance to understand this.
So I'm pretty sure, I think up to here we are pretty good. So we see some maxima for certain kinds. So this one here for the aluminium. Also, I didn't tell you the full truth. We looked at the sonoluminescence, and not always we get erosion when we get light, and not always we get light when we get erosion. So there is no correlation between light emission and erosion. So the shock amplification probably does something with the bubble interior. What is the exact cause of the erosion? We still don't know.
We have the feeling that the erosion is due to the jet, and maybe jet and sonoluminescence is not directly linked. But maybe I'm wrong.
So the main jet is not doing this. I show you a bubble which looks very dangerous. This doesn't do any erosion. This is gamma 0.5 or so. You see there's also still a liquid film all the time around it. And here, now we look from below. The jet comes in the center. And then you have this torus. And the torus also collapses, but it doesn't amplify. It also creates shocks, but they don't amplify and don't walk around it. So I think the torus has to be sufficiently small that you get this amplification, and at one spot must come in.
Thank you. I think there was a question here first.
Yeah, this is a wonderful talk, really amazing work. I have a question about, you said something about cushioning when gas would dissolve into, it was in a response to a question from the audience.
Yeah.
Do you have any evidence for that? Is that?
So there's work done in liquids with a higher temperature. Then you have a higher vapor pressure, and that leads to much milder collapses. What you look at is the re-expansion of the bubble after the first collapse, because most of the energy is lost by emitting the shock wave from the first collapse. And if you have cushioning, the bubble re-expands larger because it lost less energy in the shock wave. So larger, and that has been seen for increased gas gas content, you get a large expansion.
So it's in the expansion phase. Okay,
Yes.
very good.
Yeah.
Thank you very much. Great. Yeah.
I think Sasa had a question.
Thank you very much. I understand that the talk was about what's happening in liquid and what's happening with bubble. But as to erosion, that is another story. This is what's happening with substrate. And I couldn't understand how shock wave can damage substrate. Because I understand about jet. Jet is localized, or it's like needle. As you said, it's making a hole, and this is what. But shockwave, it could be bigger. So, is it by melting? You mentioned melting, or what's that?
Good point. So, I want to emphasize the needle jet, this fast jet, is not doing any damage because it happens at a different location as we see or observe the damage. We only see a damage where the shockwave focuses back on one spot. And there you have a little bit of a gas pocket, which is then compressed by this focusing amplified shockwave. What happens there, we don't know. But what we could do is go at a free electron laser, or we have started with some experiments, but you can do it by using X-rays and look at the structure of the material. We use silver single crystals and use scattering of X-rays at the crystal structure together with an image of the fluid mechanics. Maybe one learns then a bit more about it. But yes, this is still an open problem. What causes erosion, I haven't told you. I told you only that you get erosion only when you have shock amplification. So yes, it's not solved the problem.
Good. I don't know if there will be any other question. Well, if not, let's thank speaker again.